Okay, the first calorimetry problem we're going to do is a dissolving of a solution. And what we've got is we're looking for the delta H of the reaction. So, bottom line is if we read it, we've got this many grams of sample, etc. And what happens is that since this is a Q problem, and remember Q is equal to mass times specific heat times the change in temperature. Q is always that value. So what we're doing is that we're looking for the Q of ammonium nitrate by looking at the Q of water. And when we relate two Q's, remember we're transferring, one of them has to be negative. It doesn't matter which one you put it on. For some reason, by convention, we just all tend to put it on the second one, but it doesn't matter. So what we're really looking for is a Q problem. So if that's the case, what we're really starting with is Q of water. Well, we have a mass of water, 55.0 grams. Now, somebody might say, hey, wait, we got two more here, but this isn't water. This is strictly the Q of water, so we're looking for the grams of water. And what we've got here is specific heat of water, which is 4.184 joules per gram per degree C, times delta T. Well, delta T, remember, is T final minus T initial, which in this case, our final is 13.34 degrees C, minus our initial, which is 26.48 degrees C. So our change in temperature here is minus 13.14 degrees C. So what we're going to do is come back in and put that number in. Now, don't change signs. Use the signs you need to use. So we'll simply run the math and we get minus 3023.7768 joules. Now, over here we specified that the Q of water is equal to the Q of ammonium nitrate, and we said one of them gets a negative. We happen to put a negative on that one. Doesn't matter. So what this means is that we have a negative on a negative. So what we have is that the Q of ammonium nitrate is equal to a positive 3023.7768 joules. Wait a minute. That actually makes sense because our temperature dropped, which means that energy is being absorbed out of our water by our ammonium. So the process of dissolving ammonium nitrate is endothermic. This is actually one of the reactions that can be found in a cold pack, which is why it goes down. Now, so let's go back and see what we're really looking for. What is the heat of solution expressed in kilojoules per mole? So what we have here is joules. We need it in kilojoules. So because I've written the endothermic there, that wasn't convenient. So I want it in kilojoules per mole. So I'm going to start with my amount, which is 3023.7768, and because I want to make sure I've accounted for stuff, we know that there are 1,000 joules in 1 kilojoule. And let's go back and look at this. Wait a minute, we need it per mole. So that means this number is associated with a given amount, which is 2.034 grams of ammonium nitrate. Okay, so that many grams gives off that. Now, a more generic unit is the grams per mole. So we've got our conversion of joules to grams. Now we need to go grams to moles. Well, we've got grams on the bottom, so we're going to need grams of ammonium nitrate on top and over 1 mole. That's the molecular weight. So we look at our handy dandy periodic table, and we determine that the molecular weight is 80.04344 grams. So when we run the numbers, okay, we're going to end up with 118.99385 kilojoules per mole. Okay, now we've got our value. Let's go back and look at our numbers. We've got 3 significance here, figures here, 4 here, 4 here. So we're going to report this in 3 sig figs. So 119 kilojoules per mole. And because this is an endothermic reaction in thermodynamics, it's much more common to actually put the positive on there, so we know that this is an endothermic reaction. So this is the first simple calorimetry problem.